Hey, welcome back, folks. We're talking about dynamics and moving into section 15.3, the acceleration of rigid bodies on a plane. And I wanted to take a moment and, first of all, hand you a bank of equations that are a pretty cool shortcut, and then recap where we are and talk about where we're going. So what this is just a table of 6 equations that allows you to do partial cross products and keep track of the sign. So when you cross I cross j, you get k. And as an example, if you had I and nothing else, and then j and nothing else, then you get I cross, or I times j is in the k direction, and that would be 1, if you will, and then nothing else. And then similarly, like if you reverse that, then you would get the negative. So it's a very handy table for keeping track of partial cross products. I highly recommend that you make a copy of it. Okay, so in 15.1, right, so 15.1, we were looking at rotation about a fixed axis. Rotation, by the way, you should take notes on this. Seriously, this will help. A fixed axis. Okay, and what was that? So imagine something. Let's put it over here. So we got a thing, right, and it is rotating. And let's make it bigger and put stuff on it. It has a length of r, like this. And maybe we've got colors, right? So we like to use red for acceleration. So maybe it's got an acceleration alpha and a rotation omega. Okay, and some v, like this, that would be orthogonal to r, and some a, I guess I should go back to blue. Let's go back to red. All right, like this. Okay, and that is a, and the formulas that we needed for that come from the relative motion, but what we found was that v is equal to omega cross r, right? So these are our vectors. Our scalars, so let's see, put these in vectors here, and scalars will make another column, although I think in this case there's only one. So the vectors are there. The scalars, this is just v equals omega r. Right, so that's how we calculate the magnitude of it. And if we're in a plane, then it makes total sense, right? Because then these are all directional. And so that's VA is equal to A sub t minus A sub n. Right, now this is actually plus, but it becomes alpha cross r minus omega squared times r. And these are the vectors. So not too bad. We got through it. Gets a little busy when you have to calculate that stuff, but this is a fixed axis, right? Nothing was really moving around. Then in 15.2, we started combining translation with rotation, right? So 15.2 was general plane motion, right? So what we learned was that we can translate or we can rotate, and if we're doing both, then it's what we call general plane motion, which is some mix of the two. And we started with the relative velocity method. Relative velocity, there we go. And that was VB is equal to VA plus VB with respect to A, right? And this is also expressed as VA plus omega cross R. And then this is RB with respect to A, right? Where these are the same thing, right? So this right here implies that VB with respect to A is equal to omega cross RB with respect to A, right? So this was our relative velocity, and I'm going to say method here. And there we go. We also learned about the instantaneous center of zero velocity. Learned about that method, and that was a pretty cool shortcut because what it allows us to do is to disregard the translational component, right? So what we end up with is VB is equal to omega cross R, but in this case R is the position vector between B and some C, which is the instantaneous center of zero velocity, right? So that is a point that we can find that is orthogonal to the velocity vectors, right? So if you get 2 points like this, one is going this way, one is going, say, this way, then you come out normal to them like this, and it allows you to skip the consideration of that, and then it's just a matter of solving the triangle. So that's where we have been, and now in 15.3, in our final chapter of this general plane kinematics saga, 15.3, let's see, hopefully you guys can still see this, we are going to look at this equation here. So basically what we're doing is we're gonna take the time derivative of this guy right here. That is what we're doing, and we're going to regard this as this guy right here. So A of B is equal to A of A, right? So the acceleration of some point A plus, and then the, I wrote it down here, A sub D, A sub N, and rather than just writing those, I'm just going to get right to the good part, and so this will be A cross R, and then minus omega squared R, where these are all vectors. So that's where we're going, and where we've been. The logic of the things, I think it's pretty straightforward, but we will start to hammer this out in the next video. So make sure that you grab all of these equations. You're going to need them, and we will play with this equation in future videos. So I hope this proves to be helpful, and I will see you in the next one.